let me recapitulate whatever that I did in my last class. We discussed full wave rectification using center tap transformer. We found that one diode conducts at a time. Okay, the one diode conducts at a time, and the voltage rating of the diode is twice the peak value of the secondary voltage of the transformer. See, why am I saying one diode conducts at a time? In other configurations, there may be more than one device conducting at a time. See, these are the issues that have to be discussed, or these have to be taken into account while calculating the efficiency. See, one diode conducts, so at a time, so the voltage across the diode is of the order of 1.5 volts or so, depending upon the power rating. So, if the input voltage itself is low, more than one, if the two diodes are conducting 3 volts is a drop across the diodes. So, if the input voltage is high, that 1.5 volts or 3 volts may be an insignificant value. So, it all depends on the input value of the voltage and the number of devices that are coming in the main path of the power flow. The second one is a common cathode configuration. We found that diode whose anode potential is maximum will conduct. The third point, in common anode configuration, diode whose cathode potential is least will conduct. Okay. Then in uncontrolled bridge, single phase bridge, we found that two diodes conduct at a time. Voltage rating of the diode is peak of the input voltage. So, just the opposite. In full wave rectification using a center tap transformer, one diode conducts at a time, voltage rating is twice the peak of the secondary voltage, whereas here two diodes are conducting at a time, voltage rating of the diode is peak of the input voltage. Okay. We also discussed two configuration in single phase semi-converter. In case 1 shown here, two thyristors are in the same leg and two diodes are in the same leg. Alpha to pi T1 and D2 conduct. From pi to pi plus alpha, D2 and D3 conduct. When these two diodes conduct, voltage applied to the load is 0. Source does not supply power to the load. When freewheeling diodes D2, D3 are conducting, source does not supply power to the load. Source supplies power only when T1 and D2 are conducting in the positive off. Okay. Yes, source supply power even in the negative off when T4 and D3 conduct from pi plus alpha to 2 pi, and from 2 pi to 2 pi plus alpha, again D2 and D3 conduct. Okay. Load current is unidirectional, whereas source current flows only from alpha to pi in the positive off and from pi plus alpha to 2 pi. It is almost a square wave. If I assume the load current to be a constant and ripple free, source current is going to be a square wave. Okay. So, what conclusion did we draw in the last class? Conduction period for thyristors is pi minus alpha radians. So, as alpha increases, we found that the duration for which thyristor conduct also reduces, whereas the conduction period for diode is pi plus alpha. as alpha increases, conduction or the duration for which diode conducts also increases. So in other words, average current rating of the thyristors is less compared to that of diode for any value of alpha other than 0. The average current rating becomes same only when alpha is 0. Okay. In the case 2, second case, we have two thyristors forming a common cathode configuration. So we have almost a symmetrical configuration, thyristor and diode in one leg, even another leg we have another thyristor and a diode. Okay. Again in the positive of at alpha T1 and D2 are at alpha T1 is triggered, from alpha to pi T1 and D2 conduct, source supplies power to the load. At pi plus alpha T3 and D4 are triggered. So what happens from pi to pi plus alpha? We have a common anode configuration here and two uncontrolled devices, remember, whereas we have a common cathode configuration, but then both are controlled devices. So till you trigger them, they behave as if they are in forward blocking mode, they block the voltage. So since we have two uncontrolled devices forming a common anode configuration, the diode whose cathode potential is least will start conducting. So D4 starts conducting at omega t is equal to pi plus. So therefore from pi to pi plus alpha, current freewheels through T1, load and D4. So again from 2 pi to 2 pi plus alpha, current freewheels through T3 and D2. So waveforms of output voltage, the source current are the same, only thing is the device, all the devices conduct or duration for which the device conduct is the same. Okay. Average value of the output voltage, we found that is always positive. It is given by Vm by pi into 1 plus cos alpha, where alpha is the triggering angle, can take a value anywhere from 0 to pi radians. Okay. When it is 0, it is equivalent to a uncontrolled bridge. When it is pi is equal to alpha, output voltage is 0. Okay. Sorry, when the trigger angle alpha is equal to pi, output voltage is 0. Now what is the displacement factor? Or the displacement angle is the angle between the fundamental component of the input voltage and the fundamental component of the source current. We found that this angle for off controlled bridge or a semi-controlled bridge is alpha by 2. So displacement factor is cos minus alpha by 2. This minus sign indicates that power factor is lagging, sorry, displacement factor is lagging. So how do we turn off either T1 or T3? So T1 is turned off by turning on T3. So when we turn on T3, a negative line voltage, input voltage appears across T1 and in turn turns off the conducting thyristor. Hence the name line commutated converter, because the input line voltage itself is used to turn off the conducting thyristor. Hence the name line commutated converter. Okay. So how many pulses are there in one cycle from 0 to 2 pi? There is one pulse from alpha to pi another pulse from pi plus alpha to 2 pi. So there are 2 pulses in one cycle. So therefore this converter is also known as 2 pulse converter. Okay, this is also known as 2 pulse converter. Yeah, I have to show something for you. So here is a single phase uncontrolled bridge. There are 4 terminals. These 2 are input, positive DC bus, negative DC bus. Current rating is 25 amperes, 600 volts. When I am saying 25 amperes, it can carry 25 amperes of current and it can block 600 volts. So input voltage theoretically peak value should not exceed 600 volts. These are all ideal values, theoretical values. Here is a high current, high voltage thyristor. See the size. It can carry 400 amperes and it can block 2 kV cathode, anode. It is generally mounted on a heat sink, and this is a gate signal wire to supply the gate current. See the size of the cross sectional area of the conductor that is used to supply the gate current. It's very thin, very thin. So very small current that is required to turn on an SCR. See the see the cross sectional area of the conductor that is used for the cathode circuit. The main power flows in this conductor, whereas a small current is flowing through the gate. Very small current is flowing through the gate. Okay, it can carry theoretically, as per the rating, 400 amperes and it can block 2 kV. So you can use in any circuit wherein the voltage does not exceed 2 kV at any given instant. Okay. These are theoretical values, but the values that should be taken into account while designing, we will discuss at the appropriate time. All those issues we will discuss. What is another issue we discussed? Now let me discuss about RLE load and current is continuous. Okay. I said if the current is continuous, whether the load is RLE or not, alpha minimum can be 0. In other words, diode starts conducting, diode that is coming in the forward path or in this bridge. If I have an uncontrolled bridge, diode D1 and D2 will start conducting at the positive 0 crossing. Okay, and if I have, since I have a thyristor here, I can trigger this thyristor at alpha is equal to 0, independent of the load. If current is continuous, remember thyristor can be triggered at alpha is equal to 0 at the, okay. But then what happens to the current, whether current is increasing or decreasing, or how that is possible? Take for example the equivalent circuit when T1 and D2 are conducting. So the equivalent circuit is given here. Source, we have a source, T1 is a short circuit when it is conducting, R, L and E, D2 back to source. Okay. Current is continuous, so this is the path KVL has to hold good. So KVL gives VI is equal to R into I plus L di by dt plus E. So therefore di by dt is VI minus E minus Ri divided by L. So if I neglect R, it is given by V minus E divided by L. So di by dt is positive when the instantaneous value of the input voltage is higher than E. Okay. So remember, I might have said yes, if the current is continuous, thyristor can be triggered at the positive 0 crossing, that doesn't mean that di by dt is positive. So first thing that comes to my mind is when in the positive of T1 and D2 are conducting, when I say that, I can assume that current may be increasing, or in other words di by dt is positive. It is not necessarily true. If the load is, even for that matter, even if the load is RL or RLE, di by dt need not be positive, or it is not positive the moment you trigger the thyristors. Okay. It all depends on the value of L, it also depends on E. So in this case we found that till omega t is equal to sin inverse E divided by Vi, E is greater than Vi, so cathode potential need not be, so di by dt is always, di by dt is negative till this region. Okay. So here, see the waveform, voltage, the current, I might have triggered, so current is flowing, di by dt is decreasing. So at this instant it starts increasing, of course, provided R is 0. If R is finite, it is beyond this region, beyond this point, current starts increasing. Okay. Current increases again at this point, again Vi minus E divided by L, they are equal, so di by dt is 0, that means it has peaked, it starts decreasing. So current is, how the current is flowing, even though magnitude of Vi is less than E, it is because of L di by dt, and L di by dt is negative, di by dt is negative, current is decreasing. Okay, this is the condition. The problem starts, what happens when the current is discontinuous. If the current is continuous, you don't need to know the type of load. You can trigger the thyristor wherever you want. So di by dt is positive or negative depends on instantaneous value of E and the load parameters. And when the devices are conducting, input voltage is same as the output voltage, or V naught is same as Vi. Okay. And if the freewheeling diodes are conducting, output voltage is 0. You don't need to know the type of load at all if the current is continuous. The problem starts when the load is discontinuous. Things are not very straightforward, listen to me carefully. One assumption that I am making is, assume that I becomes 0 after pi. Okay. I am assuming it. See, need not be, current may become 0 anywhere. See, it's attained a peak value here and it starts decreasing. If I have a high value of E, current may become 0 much before pi. Okay, much before pi. It's all, what you need to find out is, we need to know the value of L, E and R. Positive L di by dt should be equal to negative L di by dt, and equate the areas or solve the differential equation, and you can find out where exactly you can find out the point at which current becomes 0. Yeah, I am assuming that current becomes 0 after pi. Okay. After pi. Okay. So at alpha, which is higher than sin inverse E divided by Vm, I am triggering T1. Okay. The moment I am triggering T1, they starts conducting, T1 and D2 starts conducting, source supplies power to the load, current starts flowing. Okay. What happens at omega t is equal to pi plus. In the upper half we have a diode and a thyristor forming a common cathode configuration. So omega t is equal to pi plus D3 gets, or anode potential of B is higher than the potential of A. So immediately D3 starts conducting, T1 turns off. Okay. In the lower half, T4 is not triggered, it gets triggered only at pi plus alpha. Till then this is in the blocking mode. So current starts flowing through the load D2, D3. In other words, load is freewheeling through D2, D3. Source current is 0. See? Source current is 0, source current is 0, and load voltage is also 0. If the current is continuous, D2 and D3 would have continued to conduct till you trigger T4. Okay. The moment T4 starts, the moment you trigger T4, D3 starts conducting and source supplies power. Unfortunately, in this case, current has become 0 much before you trigger T4. So what happens now? What is the load? What is the voltage appearing across the load? Listen to me. If the load is passive, there is no current, so there is no voltage. Since we have considered load to be RLE, voltage appearing across the load is E. So the instant from the current becoming 0 till you trigger the other thyristor, that is T4, voltage applied to the load is E. Okay, see here. Somewhere at this instant current has become 0, next thyristor is triggering only at pi plus alpha. So from this instant to pi plus alpha, voltage appearing across the load is E. At pi plus alpha, you trigger T4, D3 starts conducting. Okay, voltage applied to the load is again the input voltage, a sinusoid. Okay. So the load current, the unidirectional, source current. Sorry, the source current is 0 here. It should have been. This is the source current waveform. Okay. So you should be extremely careful while drawing the load voltage waveform when the current is discontinuous. You need to know the type of load. If the current is continuous, you don't need to know the type of load, because the load voltage is either the input voltage or 0. It depends on whether the thyristors are conducting or the freewheeling mode. Okay. Now we discussed case 1 and case 2, two different configuration, two thyristors in one leg, and in the second case is one thyristor and one diode in one leg. Okay. Other than gamma being not the same, what are the differences between these two? What is the difference between these two bridges, or when do you prefer? What I said, both are line commutated converters. Line voltage is used to turn off the conducting thyristor. Remember, I discussed this point in the while discussing the devices, that device should be completely turned off before it is forward biased again. I'll repeat, device should attain its blocking mode before it is forward biased again. Okay. What happens in case 1? At omega t is equal to pi plus D3 starts conducting in the positive of omega t is equal to pi plus, in this sense positive of ends at pi, at omega t is equal to pi plus D3 starts conducting, is independent of the instant where you trigger T1, whether alpha is 0 or alpha is pi by 2 or alpha approaches pi, does not matter. At omega t is equal to pi plus D3 takes over from T1. Okay. What happens in case 2? We have a common anode configuration in the lower half. Assume that alpha approaches pi. Okay. Alpha approaches pi. So somewhere nearing pi you want to trigger T1 in the positive half. Prior to T1 triggering, current was flowing through D2 and T3. So in the positive half, since alpha is approaching pi, so entire positive of T3 and D2 were conducting. So load voltage is 0, current was freewheeling through T3 and D2, source current is 0, almost the entire part of the positive of. At omega t approaches pi, you want to trigger T1. Okay, you have applied a gate signal to T1 somewhere approximately near to pi. T1 tries to turn on, so potential of A is same as the cathode potential. A small positive voltage appears across T3. A small negative voltage appears across T3 because potential of B is slightly higher, slightly less than potential of A. I will repeat, when you have triggered T1, potential cathode potential of T3 is same as potential of A. Alpha is approaching pi, we find that potential of A is approaching 0, same as potential of B also is approaching 0. At omega t is equal to pi, both are 0. Okay, so as you approach the negative 0 crossing, voltage appearing across, the magnitude of voltage appearing across T3 also reduces. A small negative voltage is appearing across T3. Okay, the device is, in principle, it is reverse biased, trying to turn off. I said device is non-ideal. It will take its own time to turn off. Basically, thyristors are slow devices. As it tries to turn off, at omega t is equal to pi plus, again a positive voltage appears across it, isn't it? At omega t is equal to pi plus, what happens? Potential of B is higher than potential of A. Okay, we might have triggered T3 just near the negative 0 crossing, a negative voltage appeared across T3, device is trying to turn off. At that instant, maybe instantaneous value of the input voltage becomes 0, omega t is equal to pi plus, and immediately after that potential of B becomes higher than potential of A positive voltage appears across T3. Unfortunately, it may so happen that T3 may not have attained a positive blocking capability. So, it was trying to turn off, some current was flowing, current was decreasing, immediately it is started getting forward biased. So, therefore, T3 continues to conduct, T1 cannot turn on. Is that okay? It was trying to, T3 was trying to turn off because you have triggered T1. T1 was trying to turn on, T3 was trying to turn off, but then as it was turning off, it was getting forward biased. So, some sort of a commutation failure we have here, thyristor does not turn off, so it continues to conduct, T1 does not turn on. So, what had happened from 0 to pi till 0 to alpha, where that alpha was approaching pi, current was flowing through T3 and D2. Current was flowing through T3 and D2. At omega t was approaching pi, you triggered T1, and I told you that T4 did not turn off. We had some sort of a commutation failure there, and again it starts conducting in the entire half cycle. Now, T3 and D4 starts conducting at omega t is equal to pi plus, because in the lower half we have a common anode configuration. D4 immediately starts conducting. This was trying to turn off, it did not turn off, it continues to conduct. So, we have a powering mode now. There is power flows through T3, load, D4 and source. So, the entire negative or entire pi radians T3 and D4 conduct. See the voltage waveform. We have an uncontrolled rectification, maybe as if I have only a single diode conducting for the entire pi radians, and here output voltage is 0. So, this waveform is similar to that of half wave rectifier, similar to that of a half wave rectifier. We had a source, one diode coming in series and a resistive load, or I have one source, one diode, freewheeling diode and load. If I have that sort of a configuration, I get this waveform. I will repeat, if I have a source, one diode and a load, or source, one diode and a freewheeling diode and the load, I get this sort of a waveform. This is nothing but a half wave rectification, hence the name half wave effect. So, in case 2, we have half waving effect, which is not there in case 1. So, remember, whatever, there are certain advantages or disadvantages. It's nothing like this is the perfect system and this is a bad system. No. Out here in case 1, the average current ratings for alpha not equal to 0 is not the same, or conduction period for the device is not the same. Whereas in this case, conduction period, conduction duration for all the devices is the same, but then as alpha is approaching pi, we have a half waving effect, whereas this effect is totally absent. Okay. So, certain plus points, certain minus points. That's the way the life is all about. Okay. We have certain plus points, certain minus points. There is nothing like this is the perfect system and this is a totally a useless system. In nature, somehow in nature we do not have such a system. Let's solve some problems. We'll start from simple problems, then we'll increase the complexity. Maybe if you try to solve this problem, you may be able to appreciate the subject more. Okay. A simple problem here, half-wave rectification, half-wave controlled rectification with a freewheeling diode. I have put a thyristor, one diode or LE load. Okay. The problem says L is large. Okay, L is large. The moment when I say L is large, the first thing that should come to your mind is current is continuous. Okay. When someone says that L is large, you can safely assume that current is continuous, because we know that current cannot change instantaneously, so L is very large. First of all, L is very large, so you can safely assume that current is continuous. The moment current is continuous, I am telling you, problem solving is going to be very simple, because I know that when the thyristor is conducting, output voltage is same as the input voltage. If the freewheeling diode is conducting, output voltage is 0. The problem starts when the current is discontinuous. Okay. So, okay, fortunately L is current is continuous here. So the problem is find the value of alpha. What should be the trigger angle if the average value of I is 100 amperes? The average value of I is 100 amperes. Okay, how do I solve that problem? Okay, I will plot the input voltage, which is a sinusoid. This is the value of E, which is 20 volts. Input is 230 volts, 50 hertz, single phase supply. So this peak is around 230 into root 2 is of the order of maybe 325 volts. E is 20 volts, so somewhere here. So L is large, E is very small, R is also very small. So there are very good chances of current becoming continuous, because as this value of E comes down, okay, the duration available for the current to increase di by dt also increases. Okay, is only when instantaneous value of the input voltage is higher than E, current starts increasing. Okay. Let us assume that thyristor is triggered at alpha, current is continuous, do not worry. So the moment you trigger at alpha, input voltage appears across the load. Okay, at alpha you have triggered, input voltage is same as the output voltage, or output voltage is same as the input voltage. At omega t is equal to pi plus, since the load is inductive, current continues to flow, but then the moment instantaneous value of the input voltage is becoming negative, the freewheeling diode starts conducting, because you cannot have a positive voltage appearing across the diode, because beyond pi this potential is higher than this potential. If T conducts, this potential is same as this potential. So a positive voltage appears across diode. It is not possible. So diode starts conducting turns of the thyristor T. So, in the entire negative half, since the current is continuous, current deconducts. Okay. See, I have, if there was no diode here, thyristor would have continued to conduct. Beyond pi, a negative voltage appeared across the load, decay would have been faster. Okay. So, current would have become 0 somewhere in between pi to 2 pi. So, what I did here, I have connected a freewheeling diode, voltage appearing across the load beyond pi is 0. Okay. So, the forcing function is 0, current decays slowly. Second is, I have used a very large inductor, so current continues to conduct, and that too very slowly. What happens in the positive half from 0 to pi? If I had a diode replacing the thyristor, it would have started conducting at omega t is equal to 0 plus in the second cycle, or at steady state in the positive 0 crossing, the main diode would have started conducting. Since the current is continuous, you can trigger the thyristor at omega t is equal to 0 plus, and as soon as I trigger the thyristor in the positive half, now a negative voltage appears across D and diode turns off. So, till you trigger the thyristor, source voltage does not appear across diode, because we have a open circuit here. We have a open circuit across the thyristor, because you have not triggered the thyristor, we have an open circuit here. So, at steady state, current is continuous. Okay. From pi to 2 pi, freewheeling diode was conducting. It continues to conduct till you trigger the thyristor, even in the positive half. You can trigger it at omega t is equal to pi, omega t is equal to 0 plus, you can trigger it. Okay. So, till you trigger the thyristor, freewheeling diode continues to conduct even in the positive half. Please remember this, because we have an open circuit there, T does not conduct, it is not triggered. So, source voltage does not appear across the diode. Because we have an open circuit. Remember, don't make a mistake while drawing the waveform. If your waveforms are correct, then you need to find out just the average value of it. You have to integrate it. Anyone can do, even 11th standard or 12th standard student can do. Okay. The first thing is you need to understand how the circuit works, draw the waveforms. Having drawn the waveforms correctly, you are through, you are done. Let me tell you one thing. You can afford to make a mistake while integrating. As a teacher, I may not deduct any marks if you make a mistake while integrating. But then, since it is because it is not a course on mathematics, it is a course on power electronics. Fine, you can make a mistake. You can afford to make a mistake. I may try to overlook that mistake. But then, since it is a course on power electronics, I would expect you to draw the correct waveforms. If the waveform is correct, I know that a student knows the subject. Okay, he must have made a silly mistake in a hurry, he might have made a mistake while integrating, it's pardonable. Okay. So, the first point is draw the waveforms, try to understand the functionalities, how the circuit works. The second is draw the correct waveforms, you are done. Your problem. Okay. Current drives. So diode continues to conduct. So at steady state, okay, n cycles are over. From 0 to alpha, D1 is conducting. From alpha to pi, thyristor starts conducting, and n pi to n pi plus 1 alpha, D1 continues to conduct. When the source supplies power so only when thyristor, main thyristor is conducting. Okay. So thyristor conducts from alpha to pi. So there is only a one pulse in one cycle. There is only one pulse in one cycle. Even output voltage also, there is only one pulse in one cycle. So half wave rectifiers, they are also known as single pulse converter or one pulse converter. Okay, one pulse converter. So before solving, we try to see the source current waveform. Okay, the moment diode starts conducting, source current instantaneously becomes 0. Okay, when the thyristor is conducting, load current is same as the source current. It is. So the moment thyristor is triggered, diode turns off. Whatever the current that is flowing through the diode starts flowing through the thyristor. So instantaneously it jumps to the load current, increases, follows the load current, reaches a peak, then starts coming at pi omega t is equal to pi plus d starts conducting. Immediately T1 turns off. Okay, this is because I am assuming, in the beginning of my course I told that let us neglect the source inductance. Okay, if you take the source inductance into account, what happens we will see sometime later. Let us not worry now. So source supplies power only in one cycle. There is only one pulse per cycle. Input is a sinusoid, a pure sinusoid. Current is a non-sinusoid, but then it supplies only between alpha to pi. There is only one pulse. So if I try to take the Fourier series of this waveform, it has a average component. In other words, a naught plus the sigma an into cos omega t plus bn into sin omega t. So if I find that a naught is finite, it has an average component. Average component nothing but a DC component. Average component is nothing but a DC component. So I am drawing a DC component from the source. I will repeat, I am drawing a DC component from the source. What happens when I draw a DC component from the source? After all, this current has to come from the transmission line, transformers, secondary, it has to flow through the secondary transformer. What happens? We will discuss this point in detail. I will solve a very interesting problem sometime later. A very interesting problem, like putting a diode across the transformer, putting a diode in the secondary of a transformer. Apart from the average component, it has other frequency components also. Write a Fourier series, a naught plus an cos omega t sigma plus bn sin omega t. You will find that it has other frequency component also. Only the fundamental component, that b1 sin omega t, is responsible for power transfer, because input is odd function, that is some sin omega t. So source current, which component of the source current whose frequency is same as omega and is sinusoidal, which is responsible for power transfer. the remaining higher frequency components flow in the transformer secondary transmission lines. The effect of higher frequency components, these higher frequency components are also known as harmonics. Henceforth I will say the higher frequency components as harmonics. These are nothing but higher frequency components which are present in the source current, will definitely affect the source and other circuits. The effect of harmonics on other circuits we will discuss in detail sometime later. Okay. So we found that. Now let's solve this problem. Source current flows from alpha to pi, load current is continuous, increases, decreases. How do I solve? We said average value of the current is average voltage applied to the load minus E divided by R. Are you with me? Average value of current depends on the difference between the average value of the output voltage minus E. In other words, V average is equal to I average into R plus E. L divided by dt average is 0. Okay? It is only R, E and V average will determine the current flowing in the circuit, which will determine the average value of the current. So average value of I is average voltage across R divided by the value of R. Value of R is given by 0.01 ohms. So average voltage across R becomes 1 volt, since average value of I is 100 amperes. Okay. This is the equation. V average is equal to I average into R plus C. So therefore V average is 21 volts, isn't it? E is 20, I average into R is 1, therefore V average is 20. Now what is the average value of the output voltage? 0 to alpha, it is 0. Alpha to pi, it is Vm sin omega t, and pi to 2 pi, it is 0. So 0 to pi, alpha to pi, Vm sin omega dt, Vm is 230 into root 2, 1 plus cos alpha. So alpha equated as 53 degrees. Okay, alpha is equal to 53 degrees. So by solving this problem, I have brought out various issues. One is, in a half wave rectifier or single pulse converter, average value of the source current is finite. In other words, we are drawing a DC component from the source. Also, there are high frequency component in the source current. Effect of DC, effect of high frequency component in the source, we will discuss sometime later. Okay. If there is a controlled device here, freewheeling diode conducts even in the positive half cycle if the current is continuous. Remember, if the current is continuous, freewheeling diode conducts even in the positive half till you trigger the thyristor, because till you trigger the thyristor, source voltage does not appear across the diode. Okay. So if the current is continuous, it's only when the thyristor is conducting, input voltage is applied to the load, and for the entire remaining entire duration voltage applied to the load is 0. Okay. Thank you.